Well, hello again. Welcome. We're going to move on to series and sequences. Maybe I should have said sequences and series. I'm going to do sequences first and then use them to work out how to deal with series. So I haven't said what these things are. I'll deal with series later. Let's just talk about sequences. So a sequence is just a collection of numbers in order separated by commas. So you could do something like this. The dot dots mean that this is an infinite sequence. It goes on forever. Well, often these things are specified by formulas. So if I write an is sine of n over n squared, then this defines a sequence that you get by plugging in n equals 1. So you get sine 1 over 1 squared. And then n equals 2, sine 2 over 2 squared. Sine 3 over 3 squared, it's for n equals 3, and so on. So it's a rule. If you like, you can sort of simplify it to sine 1 over 1, sine 2 over 4, sine 3 over 9, and then hope that the pattern 149 is seen, but I actually almost prefer it in the top sense. Okay, so that's a sequence. What can you do with a sequence? Well, you can take the limit of the sequence. So what I'm thinking is that suppose you draw a graph. Now, unlike a regular function, if I draw the n-axis here, and then this is going to be the an-axis, the only values that n is allowed to take are 1, 2, 3, 4, 5, just the integers. So it's not, there's no way this thing can be continuous. On this a-axis, I write sine 1 over 1 squared, so it would be this point here. Sine 2 over 2 squared is down here. Sine 3 over 3 squared is down here, and so on. We find that it looks something like this. And I'm not going to join these, because as I said, n can only be 1, 2, 3, 4, 5. It has to be a positive integer. But nevertheless, it still looks tempting to join it. So if I do join them, this would not be the n-axis anymore. This should now be called the x-axis, and this would be the function, not the sequence, but the function f of x is sine x over x squared. So this sort of completes the dots. It connects them in a nice, continuous, and smooth manner. Now, the whole point is we'd like to say limit as n goes to infinity of sine n over n squared is equal to 0. What that means is when n is very large, the quantities sine n over n squared are very, very close to 0, and they stay there. They approach 0. They get arbitrarily close to 0. Well, this is very similar to this sort of statement. Limit as x goes to infinity, sine x over x squared is 0. This one we've already looked at, we already understand. The only difference between this and this is that in this case it is understood, well, the variable n, I don't know, it has to be clear that we're in the context of a sequence, but n just goes up to infinity via 1, 2, 3, 4, 5, 6, and not via one of the smooth sort of transition. So there's not a lot of difference. So unsurprisingly, there's a lot connecting sequences and functions. So let's take a look at a few of the things here. By the way, I haven't really defined the technical meaning of a statement like this, that the limit of the sequence is L. But you can look in Appendix A for the real technical details. I mean, I didn't actually define this for a function either, but as long as we have an intuitive understanding, we can actually do quite a lot. This means that when n is very large, as you progress along the sequence, the values get very, very close to L, and they stay close after some point. How close? As close as you like. All right. So what I have said is that this function and the sequence have a lot in common. So one thing that you can do with sequences that you can also do with functions is, as I've said, take limits. And so here's the general principle that I'd like to espouse. Okay, check this out. If the limit as x goes to infinity of f of x is L, then the limit of the sequence whose values are f of n is also L. And here I'm thinking this as a continuous function. It actually doesn't necessarily even have to be continuous, as long as it's, well, anyway, let's just say it's continuous. And here I'm thinking of this as a sequence. All right, so if a function has a limit, then the sequence that's formed by ignoring everything of that function except at the integers, the positive integers, also has the same limit. The converse is not true. That's what I mean is if I happen to have a sequence that converges, has limit of L, well, the values could look something like this. They're increasing, in this case, up to this number L, and so on. Do you think that any function that joins it has to have a limit of L? Actually, no. I could do something very sneaky and have the function just come and visit at these points. And from the point of view of the sequence, it never knows about these little detours that the function is making. The function doesn't even have a limit. And yet the sequence has a limit. So it's not true that if a sequence has limit L, then any function joining those points will have limit L. But it is true in reverse. If the function works, then the sequence must work. All right. So here's some other things that still work. The sandwich principle. Actually, even before you notice the sandwich principle, if you want to take a look at this limit that I'd written up earlier, limit as n goes to infinity, sine n over n squared is 0, one way of proving that is to prove the limit with x over x squared, and there you can use the sandwich principle. Well, the sandwich principle we already know. You trap the function in between two functions that have the same limit. One function is bigger, the other one is smaller, and they squeeze the one we want to the limit that we want. Well, we could just then use the sandwich principle on sine x over x squared. However, it also works directly on series. So maybe just for the sake of writing it down, although there's nothing surprising about it, the sandwich principle, otherwise known as the squeeze principle, in this case says, so you have this limit that you want, limit of an. So what you want to do is find a lower sequence, bn, that, and a larger sequence, cn. So b and c sort of trap a in between them. So we find them such that the limit of bn is L, and the limit as n goes to infinity of cn is also L. If you can. If you can. Of course, you can't always do that, but if you can, then the limit that you want is also L. And so without even using functions, you could just trap, for example, sine n is less than or equal to 1 and greater than or equal to minus 1. So if you divide this by the positive quantity n squared, you get this inequality, minus 1 over n squared. less than or equal to sine n over n squared, less than or equal to 1 over n squared. And then as a sequence, you can easily see that this goes to 0 and that this goes to 0 because the functions 1 over x squared and minus 1 over x squared go to 0. Or even more basically by just saying, look, when n is really large, whether or not it's an integer, 1 over n squared is really small, close to 0. And then you would invoke the sandwich principle directly on this. So it's not very exciting, but it's nice to know that it works. Another thing you can do is use L'Hopital's rule. Now, L'Hopital's rule fails utterly on a sequence by itself because it relies on differentiation. And you cannot differentiate a function that is just only defined at integers. There's nothing smooth about it. So if you do this embedding trick, you can also, you're allowed to use L'Hopital's rule. So if I told you that the sequence an is defined by log n over root n, and I ask you, what is the limit as n goes to infinity of an? Well, it almost looks right to do this. The limit that we want is, of course, the limit of log n over root n as n goes to infinity. I would love to use L'Hopital's rule, and in practice, you probably may not even lose points in Math 104 at least, if you do, but you really shouldn't. I can't guarantee that you won't. You should say embed sequence in function f of x equals log x over root x. So we've embedded the sequence in this function. Now, the limit as x goes to infinity, and I'm thinking of x as a continuous variable now, of log x over root x, well, now we can use L'Hopital's rule because it's infinity over infinity. So we differentiate top and bottom. We get 1 over x over 1 over root x, which works out to be root x over x, otherwise known as 1 over root x. And, of course, this limit is 0. And therefore, because the function has limit 0, the sequence also has limit 0. And this is not just changing the x to an n. It's what they represent. N has to be an integer, no derivatives allowed. X, on the other hand, is a continuous variable. One other little property that I think is very important, actually, is that if you have a continuous function, this will respect a limit. By respect, I mean it can swap places with a limit. So just the easiest way to state it is by example, probably. If you have the limit of cosine sine n over n squared, well, what is that? What you'd like to say is that as n goes to infinity, we've shown, using the sandwich principle, that sine n over n squared goes to 0. And so you'd also like to say that as n goes to infinity, cosine of sine n over n squared goes to cosine of 0. So you'd like to whack both sides of this arrow with a cosine. And that is allowed because cosine is continuous at 0. If cosine were not continuous, then the value of cosine near 0, which these numbers are, is not anything like the value of cosine at 0. But because cosine is continuous, this is fine. So this, of course, equals 1. So in this limit, you could actually set this problem up by saying it's the cosine of the limit. That's what I mean by respect. The limit of the cosine is the cosine of the limit because cosine is continuous. So this is cosine 0, which is 1. So the solution is all on that top line, but another way of writing that solution, which would be equally valid, would be to write those other two lines down there. Excellent. So that is the basic introduction to sequences. Anyone has any questions? Shout them out. All right. Next thing is to investigate two important sequences. One of them I won't spend much time on, but the first one is worthy of some attention. So it's called a geometric sequence. And in its simplest form, I'm going to pick a number r. So I have some number r, and I form the sequence that goes like this. 1, r, r squared, r cubed, r to the fourth, and so on. So I'll interpret 1 as r to the 0 and start the sequence at 0. So an is going to be the nth power of r, and this is from n equals 0 onwards. So actually, sequences don't have to start at 1. They could start at 5 or 0 or 7 or any other positive number. You could even start it at a negative number if you want to. But that doesn't seem to be very common. Okay, well, at least not in this course. So we have an is r to the n, and this is the geometric sequence of ratio r. So the question is, what is the limit of that sequence? Well, it depends on what r is. Let's come over here briefly and do some experiments. If r happens to be 0, it's not a very exciting sequence, rather. It's 1, 0, 0, 0. And so, of course, the limit is 0. What if r happens to be 1/2? Well, then the sequence is 1, 1/2, a quarter, an eighth, a 16th, and so on. So powers of 2 on the bottom. That seems to converge down to 0. I should have said the first one obviously converges to 0. Apart from that first term of 1, all of the terms are 0, so they go to 0. r equals -1/2 is of interest. This actually is powers of -1/2, and every second power, the minus goes away. -1 squared, fourth power, 6th power, 8th power, all +1. So actually the square of -1/2 is a quarter. And then we go -1/8, a 16th, and so on. So the sequence is alternating. It goes back and forth between positive and negative. Now this one also, however, converges to 0. It just does it from a sort of straddling 0 point of view. Points get closer to 0. Actually, these three are all special cases of the fact that this limit is 0 if r is any number less than 1 or bigger than -1. What actually happens at r equals 1 is that the sequence is all 1s. So, of course, it goes to 1. So it's 1 if r happens to be actually equal to 1, which is not very interesting. On the other hand, if r is, say, 2, then the powers are getting bigger and bigger and bigger, and so that is going to infinity. And that is symptomatic of the general case that the limit is infinite if r is any number greater than 1. Any number greater than 1, the powers increase. Now, if r equals -1, we just get the alternation between 1, -1, 1, -1. And this does not have a limit. It oscillates too much. It doesn't get close to anything. Okay, sure, it straddles 0, 1, -1, 1, -1, 1, -1. But it doesn't get close to 0. It's still far away. So this limit does not exist. And actually, even worse things happen when you let r be, say, -2. There, you get this oscillation, 1, -2, 4, -8, 16, and so on. But they're even further away from 0. They're just sort of going, back and forth, bong, bong, huge back and forth. Certainly, this limit does not exist. And so, in general, the limit does not exist if r is less than -1 or even equal to -1. And that's the complete categorization of this geometric sequence. So this will become even more important when we start to add these things up. But for the moment, I suggest that you learn this limit in the different cases. Okay, so having spent a lot of time on that one sequence, the geometric sequence, here's another sequence which I'll just state. Limit as n goes to infinity, 1 plus k over n to the power n is e to the k. Well, this is just a special case, or it follows from the same limit as x goes to infinity, but it does come up quite often. Of course, when it comes up, you often don't have a k there. You normally have some number, such as what is limit as n goes to infinity, 1 minus 3 over n to the n. Well, you'd better notice that this is a special case of this general formula, except with k equals negative 3. So this limit is e to the minus 3, otherwise known as 1 over e cubed. All right. Well, I don't really have much to add concerning sequences. Really, all the action is series. The thing is that sequences are used, as I said, to define series. As you see, sequences are just special cases of functions, actually, where the domain is positive integers, or maybe 0 and the positive integers. So, not so much new. On the other hand, series is quite new, so I want to proceed. I've covered 22.1, so now this is actually in 22.2 in my book. So soon I'm going to get onto some really practical problem-solving matters, but I need to tell you what a series is. Well, a series is just a fancy word for a sum. So what I'd like to do is start with some sequence, but just replace all those commas by pluses. A1 plus A2 plus A3 plus A4, and so on. And what does that even mean, and so on? Well, to sort of see if we can understand what's going on in a special case, let's take the geometric sequence with ratio r equals 1/2 and write it out as a sequence. Suppose I try to turn it into a series. What I'd like to do is understand what is meant by this series. So let's try to do it. Suppose I take a square of side 1. Well, that has area 1, and that's going to correspond to this first term 1. Now, my next thing is to take half the height, but still with 1. So this will have area 1/2. On the other hand, if I take half as much again, I get a square of area 1/4. And then I can repeat this with a rectangle of area 1/8, a square of area 1/16, 1 over 32, and so on. What's so on going to involve? It's going to involve carving this thing up. And I can't really finish it because the chalk will wear out. Maybe. I don't know. I can't zoom in enough. But you get the idea. Actually, this sum is never equal to 2 if you chop it off anywhere. But it's really, really close to 2 if you wait a while before chopping it off. How close? Well, if you're prepared to do enough chalk marks or go far enough, you can get it as close as you like to 2. Arbitrarily close. So I'd like to say that this equals 2. But I need to make it formal. And the way I do it is exactly by chopping it off. So let's just chop it off. The first place I could chop it off is 1. The next place I could chop it off is 1 plus 1/2, which is this plus this. Then the next one would be 1 plus 1/2 plus 1/4, and 1 plus 1/2 plus 1/4 plus 1/8, and so on. So I guess you can think of this as 1, 3/2, 7/4, 15/8, and so on. And you ask yourself, what happens to this sequence? So actually, we started off up here with a sequence. we turned it into a different object, a series, by changing the minuses to a pluses, by changing all the commas to pluses, rather. And then, by chopping it off here, and then here, and then here, and then here, and considering the sum of everything up until that point, we form a new sequence. And this is called the sequence of partial sums. Partial because we didn't do all infinity of it. We just did 1 here, then 2 there, then 3 there, 4 there, and so on. And this sequence, with any luck, has a limit. As it happens, the limit is 2 in this case, and we'll prove that soon. You can already see 15/8. If you try the next one, you'll find it's 31 over 32. 31 over 16. And then it will be 63 over 32. And these numbers are getting exceedingly close to 2. So, since this has limit 2, we're going to say that means this has limit 2. So, let me write this out in more generality. In order to define this, we're going to define the nth partial sum, capital Nth partial sum, which I'm going to call capital A, capital N. And here it is. I just chop off the sequence, or the series, I guess. So instead of going on forever, it's just the sum of capital N numbers. Nothing infinite. We know how to add up a finite number of numbers. No problem. So having defined this, by the way, we should write this in sigma notation as well. It's the sum from n equals 1 to capital N of A little n. So make sure you believe that this is the same as this. So we'd like to define, the infinite summation to be equal to the limit of this partial sums sequence. So maybe up here I should have written sequence here to remind us that capital A is a sequence, whereas the little a is now a series. We're adding them up. So I'd like to define this to be the limit of the partial sums if it exists. And so the beauty of this is a sequence, and all we're doing is taking the limit of a sequence and saying that is the limit of the series. Of course, this is a different sequence from the original one. So it's a little bit complicated. We start with a sequence, turn it into a series, and we get a new sequence. And they're all related, but they're not the same thing. By the way, this becomes almost a no-brainer if you write it in sigma notation. In sigma notation, the left-hand side is written the sum from n equals 1 to infinity of an. And on the right-hand side, we have the limit as capital N goes to infinity. And if you look up here at the definition of an in sigma notation, well, this is just the sum from n equals 1 to n of an. So this is almost a no-brainer here. The sum from n equals 1 to infinity, of course, is the limit as capital N goes to infinity of the sum from 1 to n. The important thing to understand, and the reason that I don't just write this down and say it's obvious, is that these objects here constitute a sequence. So here we are dealing with a limit of a sequence, and that is why we spent 25 minutes on sequences earlier. Now, I'll see if anyone has any questions in a second, but I kind of want to give one more metaphor for what's going on here that will become quite useful. I'm just going to imagine this sort of parallel to the board as an axis, and let's say here's 0, so that's going to be my starting point. And let's say that's forward, because I happen to be facing this way, and this is backwards. So this is positive, that's negative. All right, so I've got some dude who has a megaphone over there who's shouting orders at me and unfortunately I have to obey. So the dude is going to shout out numbers, and those numbers correspond to how many feet or steps I have to take. And if it's negative, I've got to go backwards. So, I don't know, suppose he calls out 1. Well, I have to take step 1 forward. And then he might call out a half. So I take a step a half forward. Well, where am I? I'm actually at 3 halves from the original. That's this number over here. Well, now if he says a quarter, which is the next step, I end up at 7/4, which is this number over here, and so on. So what you'll find is that the nth partial sum is where I am after n steps. So the original sequence, 1, a half, a quarter, an eighth, gets turned into a series by making me do steps of those sizes. So I guess looking at this, I'm going to regard these original numbers, or maybe these ones over here in more generality, the A1s, as the step sizes. And then the partial sum AN is where I am after capital N steps. And what you want to see is you want my position to converge somewhere. So I want to be able to say 1, then a half, then a quarter, then an eighth, a 16th, and so on. And I should be getting closer to some magic point. That's going to be the limit, provided I get really, really close to it and stay that close. Of course, it doesn't matter if I overshoot it, as long as I sort of, I don't know, keep dancing around it and start getting closer and closer to it. So clearly that's actually only going to work if my steps become more and more dainty. If I keep on blundering around with big steps, then I'm not getting anywhere. So this is the nth term test, which I'm going to talk about pretty soon. But first I want to talk about geometric series. Anyway, the point of all this is that we have some understanding of how to define these objects that we're dealing with. Does anyone have any questions? Quiet bunch tonight. You could hear a pin drop. All right. So, we move on to geometric series. This is perhaps the most important type of series. And of course it's related to the geometric progressions that we looked at not so long ago. So in terms of a reference, what do I want to say? You know what? I forgot to say one thing before I talk about geometric series. I need to point out something. I'm going to tell you a rather interesting fact. There's actually a nice proof of this in, where is the proof? I think it's 22.6. There's a proof that this diverges, in fact, to infinity. So what does this mean? This is a series, 1 plus a half, plus a third, plus a quarter, plus a fifth, plus a sixth, and so on. What I'm claiming is that that is infinite. That is a very surprising fact. Let's see what it means in terms of the steps. Here I am. Dude calls out 1. So take a step 1. Then a half. Take a step half as much. Then a third. That's a third of the original step. A quarter. A fifth. A sixth. A seventh. An eighth. So I begin taking really, really tiny steps. My question is, do I ever make it to that wall? What do you all think? Think I make it to the wall? Eventually I make it to the wall. That's the hypothesis. Well, you are right. Even though it will take me a really, really long time as my steps go smaller and smaller, I will eventually make it to that wall. In fact, no matter how far away that wall was, I would eventually make it to that wall. It might take me millions of years. I should live so long. Mind you, if you said live millions of years, but you have to just spend it taking steps, well, that would be a different matter. But in any case, this is infinite. Now, by the way, this is in sharp contrast to the same sum with 1 over n squared. This actually converges. 1 plus a quarter plus a ninth plus a 16th plus a 25th and so on converges. So if I start here and I take a step of 1, but then only a quarter, a ninth, a 16th, 25th, and so on, there's a point, a visible plane of glass, if you like, that I will never get past. And in fact, there's a sort of closest point that I'll never get past, and that's the limit. It happens to be equal to pi squared over 6 of all things, but that is beyond this course. You can get that in a sophomore calculus course, something like that. In any case, it's quite a nice little fact. You don't have to worry what it converges to. Now, the point that I wanted to make is not even so much these two facts, although they're very, very nice facts. The point is that starting at 1 doesn't really make a difference. I'm trying to get the point that if I happen to start at, say, 8, I know that this also diverges. What it means is, if instead of starting with a step of 1, and then a half, a third, a fourth, a fifth, sixth, seventh, and then 8th, 9th, I just pick it up here at an 8th. Okay, so I'm starting here, 8th, 9th, 10th, 11th. But what's the difference? The difference is just some small initial period where I walked 1, 2, 3, 4, 5, 6, or 1/2 up to an 8th. The fact that I could get arbitrarily far with those first 8 terms, all I am is set back a few feet. If I start at an 8th, I will still be able to get to the wall. So another way of thinking about it is to write this sum of all of them to be just the sum of the first 7 plus the sum starting at 8. This is just some number, finite number, nothing wrong with it. Because this on the left is infinite, this must be infinite as well. So the point is that if a series diverges, it doesn't matter where it starts. And the same thing happens with convergence. If I happen to chop it off and start at 1/25th onwards, okay, I won't get the same limit, but it will still converge because it only differs by a finite number. So similarly, you can replace this bottom by any positive number, and this obviously converges. The beginning of it doesn't matter. On the other hand, there is one little thing I want you to be careful of. If you start at 0, does that converge or diverge? Well, what does it even mean? The first term is 1 over 0 squared. And so on. Well, look, it would converge if it weren't for the first term. That first term doesn't even make sense. It doesn't make sense. You can't say 1 over 0. It doesn't mean anything. So I don't even go so far as to say that this converges, or that this rather diverges, quite the... Well, I don't even want to put a label on it other than saying doesn't make sense. Doesn't mean anything. One of the terms is invalid, so I won't say it diverges. I'll just say screw it. I don't like it. Stay away from it. All right. Any other questions before I move on to geometric series? No? All right. So as I said, these are very important. What I'd like to do is sum up the powers of R. So I get 1 plus R squared plus R cubed plus R to the 4th. This is the same thing as the sum from n equals 0 to infinity, R to the n. That's the sigma notation version of this. And so what is this? Well, suppose I let A capital N be the nth partial sum. So I take the geometric series, but I chop it off at n, capital N. You may remember from your high school days. If not, there's a proof in 22.2.1, I believe, that this is given by the formula 1 minus r to the n plus 1 over 1 minus r. You can actually write it as r to the n plus 1 minus 1 over r minus 1 as well. But this is a nicer form for what we want. What we do want is to take the limit of the sequence of partial sums an, which is given by this formula here. That's the definition that I just gave. So this is the limit of 1 minus r to the n plus 1 over 1 minus r. And now you just have to take the limit of this piece, and this piece is the only part that depends on capital N. The easiest way to deal with it is to write it as r times r to the n and ask what happens to this. And I wrote up 4 possibilities, most of them pretty nasty. Certainly, if r is greater than 1, that's infinite, so this limit doesn't exist. If r is equal to 1, we'll worry about that later. If r is negative 1 or less, then this limit doesn't exist anyway. It's actually only when r is between minus 1 and 1 that this limit is 0. So certainly, this limit is 0 if that part is 0. So it's 1 minus 0 over 1 minus r if r happens to be between minus 1 and 1. Now, if r equals 1, the geometric series is 1 plus 1 plus 1 plus 1 plus 1, which is clearly infinite. So I'll just say does not exist, or infinity, or possibly minus infinity, if r is greater than or equal to 1, or r is less than or equal to minus 1. So you actually come up with this formula 1 over 1 minus r. So, in other words, this sum is 1 over 1 minus r if minus 1 is less than r is less than 1. And that's a useful formula. And I guess we say diverges otherwise. And that's the complete picture there. So that's the theory of geometric series in a nutshell. On the other hand, we should do some examples. So you need to be able to look at a series, recognize that it's geometric or related to a geometric series, and then apply that formula. Now, rather than use that formula in that form, I propose to give you a slightly different and more useful form. See, a geometric series doesn't actually have to start at 1. You can multiply all the terms by some constant, and it's still considered to be geometric. So we ought to just be able to multiply that relation by whatever the first term is and get a correct relation. So basically, here's the useful formula. This is pretty poorly phrased. Limit of geometric series is equal to the first term over 1 minus the ratio. There it is in words. Looks a little unsatisfying without any symbols, and yet I find this is the best way to deal with it. So, let's look at some examples. Well, if you take our favorite old chestnut, 1 over 2 to the n, that's that sequence 1 plus a half plus a quarter and so on. It's a geometric series, all right, especially if you write it as 1/2 to the n. Now you can see that the ratio is 1/2. So, what's the first term? We'll just plug in n equals 0, and you get the first term of 1. And so, hey, that limit is 2. Now, one thing I did, I missed out, rather, up here, that I should add is if the ratio is between -1 and 1. Otherwise, it diverges, as I've said. Now, in this case, the ratio is 1/2, which is between -1 and 1. Excellent. Okay, so that's a pretty simple example. Let's check out this example. The sum from n equals 5 to infinity of 4 over 3 to the n. Well, make it obviously a geometric series by taking out the constant 4, isolating the nth power term, and in fact write it as 1/3 to the n. And now you can see that this is the ratio. Anything with the power n is the ratio. As long as everything else is constant, and it's just constant times number to the n, you're dealing with a geometric series. So as I've said, the ratio 1 minus 1/3, notice that 1/3 is again between -1 and 1, so everything is cool. Plug in n equals 5 to get the first term, and you get 4 times 1/3 to the power 5. This is worth simplifying. 4 over 3 to the 5 over 2/3. We can certainly cancel out 1 power of 3, and you'll get 2 over 3 to the 4 after you cancel the 4 and the 2 as well, which is 2 over 81. So this series not only converges, but we know it converges to 2 over 81. All right, let's look at a harder example. The sum from n equals 2 to infinity, 2 to the power 2n, minus 7 to the n, all over 11 to the n. Okay, this is not actually a geometric series. It's the sum of 2 geometric series. Let's see why. To deal with the first term, I've got 2 to the 2n. I actually want to think of 2 to the 2n as 2 squared to the n, which is 4 to the n. So that's a nice little trick. So write this as 4 to the n over 11 to the n minus 7 to the n over 11 to the n. So I've actually split up the fraction into 2 pieces. And so I get the sum from 2 to infinity, 4/11ths to the n minus 7/11ths to the n. Now these are both geometric series if you split them up. So this has ratio 4/11ths, whereas this one has ratio minus 7/11ths. And both of those quantities, 4/11ths and minus 7/11ths, are between -1 and 1. So we can use the formula 1 minus r. So we'll deal with the 4/11ths term. What is the first term? We'll look up here, and you plug in n equals 2, because that's the first term. So you get 4/11ths all squared. As for the second term, we have a minus in between those two. So the second term is 1 minus 7/11ths, otherwise known as 1 plus 7/11ths. On the top, you take the first term, which in this case is minus 7/11ths squared, because n equals 2. And so you can work this out, and it turns out to be minus 5 over 126. I'll leave the calculation details to you, or you can look in the book. By the way, speaking of the book, I've sort of danced ahead to section 23.1. The theory is in chapter 22, and all the examples are in chapter 23. So I'm sort of doing them in parallel to save some time here. In any case, that is how you solve this problem. Let's suppose I change it very slightly and write it down like this: 4/11ths to the n minus, say, -13/11ths to the n. Suppose we'd found out that this was the series that we were dealing with. Well, this one is no problem. It converges. But this one has ratio minus 13 over 11, which is no good because it's less than or equal to minus 1. So this series, or that part of the series, diverges, and that's enough to drag down this one with it. If you try to add up a convergent sequence, a series rather, to a divergent series, I'm afraid the divergent series wins. Perplexingly enough, if you add up two divergent series, you may still get something that converges, but only by a weird sort of trick. And certainly it doesn't happen if everything's positive, but if terms are allowed to be negative, as they often can be, you might get something wacky like this. Consider just the sum of 1 over n plus the sum of minus 1 over n. Well, I've already said that that diverges to infinity. And this clearly diverges to minus infinity. And you can't add up infinity and minus infinity. On the other hand, if you add them up like this, 1 over n plus minus 1 over n, term by term, instead of adding up the series individually, you just get the sum of 0, which of course is 0 plus 0 plus 0, which is 0. So that's kind of whacked out. Mind you, if you change this slightly, you could actually get other limits here as well. It just doesn't even have to be 0. So don't think that infinity minus infinity has to be 0. It's not true. So just beware when you're adding up two series, as you are in this case. If one of them diverges, sure, the whole thing does. If they both converge, great, so does the whole thing. If they both diverge, just be really, really careful. All right. Are there any other questions about geometric series? If there are, you know the drill. Well, what's left? We need to come up with a whole lot of tests and techniques for investigating series. If everything were geometric, everything would be great. But unfortunately it isn't. And a lot of the time, the best you can say, or the best thing you can say, is that a series converges or a series diverges, without actually knowing what it converges to, in the case that it converges. So we're going to build up a collection of tests. And the good news is there's a lot in common with these infinite series and improper integrals that we spent a lot of time covering. So this means that a lot of the work we'll do is duplicated, duplication rather, of work we've already done. On the other hand, if you didn't understand it then, you'd better make sure that you do understand it, or else it's a double whammy. You could have two problems involving, say, the limit comparison test, one for integrals and one for series, and you'll find that they're very, very similar. And if you can't do one, you've kind of lost double points. So this is important stuff. This is important stuff. What I thought I'd do is give you a little overview of the various tests for both improper integrals and infinite series, and see what they have in common. So here's a little Venn diagram. And over here, I want to put the tests for series, for infinite series. Tests. And over here, we'll call it tests, techniques, for improper integrals. And of course, this is going to be tests that work for both. So here we have, in the series camp, geometric series methods, which we've just done. We've got that formula. Then we're going to have a bunch of tests. The nth term test, which I'll do very soon. And then we have the ratio test, the root test, the integral test, which ironically sits in tests for series, not the test for integrals. We'll see why soon. And we also have an alternating series test. All these tests have no analogs in the realm of improper integrals. They are specific to series. On the other hand, in the intersection, we have the comparison test, which we saw for improper integrals. Well, there's a version for series as well. We have the limit comparison test, LCT. We have a p-test, and we also have an absolute convergence test. All of these four tests have very, very similar analogs for series, similar to the ones we've already seen for improper integrals. What can you do with improper integrals that you cannot do with series? Not a lot. There's one thing you can do. Substitution. That's not really a test. It's a technique. So there are certain problems that involve substitution. By way of, there aren't too many that we looked at, but just by way of example for that one thing, so as not to be too cryptic, I want to remember this improper integral, 1 over x log x from 2 to infinity. I guess I'll look at this again next week, but for the moment, let's just remember that we substituted t is log x, dt is 1 over x dx. And we also need to note that when x equals 2, t is log 2, and as x goes to infinity, log x also goes to infinity. T goes to infinity. So in t land, this integral becomes the integral from log 2 to infinity of just 1 over t dt. I've just substituted t equals log x. The dx times 1 over x is dt, and we're left with 1 over t. And this diverges by the p-test. So that's kind of just a review of last time, or the time before, I forget, where here we've solved an improper integral by using a substitution. And there's no easy substitution analog for series. If there is, then, well, I guess you could call it summation by parts. There's that, but that's not in this course, so I won't talk about it anymore. All right, so there's a survey of tests. Now, given the available time remaining, I suspect that I am going to just do the nth term test, the ratio test, and the root test from the right of that picture there. And then I'll cover all the other tests next time. That will be the plan anyway. We'll see how we go. All right. So, let's talk about the nth term test. I had mentioned before, when I was talking about this dude barking orders at me through the megaphone, that if my steps did not become daintier and daintier, as in get very, very small, then I didn't have much hope of converging. Right? So if I'm walking around and my steps, it maybe get small for a little while, but if there's every so often a big step that's not too small, so I can't really say I'm getting anywhere and staying close to there. See, that critical thing, even if I get very, very close and then take a step forward and a step back and then stay close, and then a million steps later, I step around again. And if I keep on doing that, well, I'm not converging to this point. I keep departing from it. It's no good. I have to stay close to that limit point where I'm converging to, or else it's not a true limit. So the nth term test basically says that if my steps themselves do not go to 0, the series, my position, if you like, must diverge. So, here it is. You are investigating a series AN, and I'll often write n equals blob to infinity. By this I mean it doesn't matter where it starts. Remember, it could be 1, 0, 8, a million, a trillion. It doesn't make a difference. So if you have this series here, so we're considering this, here is the thing. If the limit of the terms, remember this is interpreted as my step sizes, if this is not 0, or the limit doesn't exist, the series that we're concerned about, n equals wherever, to infinity, must diverge. There's no way it could converge. My positions are just not converging on anything if my steps are not tiny in the end. Now, you must never say a series converges by the nth term test. If my steps do go to 0, the series could still diverge. For example, 1 plus a half plus a third plus a quarter plus a fifth plus a sixth. My steps are becoming really, really small. They're tiny. The limit of the steps is indeed 0. And yet I still get to the wall and I get as far as you possibly want. Doesn't matter where you set your limit, your limitation, your glass panel, whatever. I'll eventually get there if you give me long enough. So, just because the steps do go to 0 doesn't mean anything. So just to formalize that, not part of the test, but a comment, if the limit is 0, that's when things are interesting. The series could converge or diverge, and that's, as I say, that's where it starts getting interesting, where you really have to do some work to see what happens. Now, another way of saying this is never say a series converges by the nth term test. Forbidden. All right, any questions about that? I'm going to do some examples in a few seconds. Okay, so let's see. Suppose we look at this. Sum from n equals 1 to infinity. N squared minus 3n plus 7 over 4n squared plus 2n plus 1. Well, there's your limit comparison test, which I haven't told you about. You could certainly whip it out once you know it, and you'd be able to solve the problem. But rather than resort to such complicated tools, we can simply use the nth term test. You see, if you just take the limit of the terms, forget the sum out the front, just take the limit of the terms. This is a polynomial over a polynomial. You can divide top and bottom by n squared or use the tilde tricks. However you want to do it, it turns out this limit is a fourth, the ratio of the leading terms, since the degrees are equal there. So you get a fourth. So what does this mean? This means that as I'm taking steps, they are some weird numbers at first. The first step, for example, is 7. And they take a little time to settle, but eventually each step is around a quarter. That means that eventually I'll get into this routine where I keep plodding over a quarter or so at a time, and of course, there's no stopping me. I'm going to keep going and going. No matter how you set your marker, I'm always going to pass it. So this series, the point is that this is not zero. So the series, that's this original series up here, diverges by the nth term test. No further work required or desired. Here's another example. Let's see. The sum (1 plus 1 over n to the n). Again, just take the limit of the term, and that's equal to e to the 1, which is e, which is not 0. So again, the series diverges by the nth term test. I'm not going to write it out again. So my steps become very close to e. A slightly different example. Let's throw a minus 1 to the n in there. To get the limit, well, in terms of the terms, the limit of minus 1 to the n, 1 plus 1 over n to the n, is what? Well, this goes to e, as we've said, but unfortunately this term oscillates. So these terms become more and more like e minus e, e minus e, e minus e, and so on. So actually this doesn't get embedded in a function, it just sort of oscillates between e and minus e. So it does not exist because of oscillation. Never actually gets to e or minus e, but it's very close. So in terms of the actual megaphone dude screaming orders at me, he's basically telling me after a while, go about e forward and then about e back, and I'm going to keep taking steps that are around 2.7 forward and back. And although I don't actually go off to infinity or minus infinity, I don't get close to any point. And so this limit does not exist. Again, therefore, this series diverges by the nth term test. If that limit over here were 0, we'd have a hope. Couldn't use the nth term test. It could converge or could diverge. But if the limit is not 0 or does not exist, automatically say series diverges. Case closed. So actually, that's all there is to the nth term test. Let me just say that it is a reality check. I think of it as a reality check. You give me a series, the first thing I do, unless it's obviously geometric or one of the other tests just springs out, somehow the first thing I like to do is at least eyeball the terms and do a reality check. Do the terms go to 0? And in those 3 cases, the answer is no. And so I don't even do anything else. I just say diverges by the nth term test. So it's a sort of, as I say, reality check. All right. Any questions about the nth term test? Well, let's move on to perhaps the most useful of all the tests. I'm going to spend quite a bit of time on this. The ratio test. Okay, let me tell you what the test says. It's quite a sneaky little thing. We have some sum n equals wherever, it doesn't matter where it starts, to infinity, an. So there's our series. Beauty of this ratio test is we're going to do something with the terms, and we're not even going to write down any sums at all, no sigmas. We're going to start off with the ratio of an plus 1 of an. That's at any point in the series, an is the nth step. This is the next step, the step after the one we're on. So we'll consider the ratio of the two, hence the term ratio test. If things have negatives, it's actually very convenient to take absolute values here. Nothing is lost. So I like to put the absolute values in even right now. And what I'd like to do is I'd like to consider the limit of those ratios as n goes to infinity. So this is a quantity that's important for you to remember, because this is the thing that you use when you use the ratio test. You always write that down. And then what you want to do is write limit as n goes to infinity, and you'll normally need a big-ass fraction bar right over here, because what you're going to do is you're going to fill in the term from the sequence, or from the series rather. So you just copy it down there. So this is the nth term from the series directly. And then you go up here and you rewrite it, but replace, every time you see an n, you replace it by n plus 1 in parentheses. You normally need the parentheses. And so you'll get some expression involving n when you've done this. And you have to somehow simplify it and muck around with it, and we'll see what to do in a bunch of examples. But when all's said and done, you hope, blah, 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 that you can find the answer. You can actually take the limit and get some number L. Well, what can we say then? There are three possibilities. If L happens to be less than 1, so you've done this ratio, if the limit is less than 1, the original series, which we haven't even touched, converges. That is enough to tell that the original series converges. If the limit is greater than 1, the original series diverges. Unfortunately, if L equals 1, or does not exist for that matter, the test has been a total waste of time. Test says nothing. You have learnt nothing. Ratio test does not work. Try something else. And I might as well say not the root test, even though we haven't done it yet. Most of the time, I think if the ratio test fails, the root test will, certainly in all the examples that we're dealing with. So, yeah, you have to try another test. And of course, we haven't seen all the tests. We won't even see most of them until next week. So, in any case, though, a lot of the time, you'll be lucky and L will be less than 1 or bigger than 1, and you will have used the ratio test to investigate the convergence. Now, why on earth does this work? Well, there is a proof in my book. I'll give you a reference. The reference for the theory and the proof is 22.5.2, but all the problems we're going to be doing come from the next chapter, it's 22.5.1. 23.3 is where all the examples are. So the theory in chapter 22 and the examples in 23. Just to give you a rough idea of what's going on, if an were actually equal to a geometric series r to the n, then an plus 1 over an would be equal to r to the n plus 1 over r to the n, which is r. So the ratio, without even taking a limit, the ratio is r. If we surround this by absolute values, you get the absolute value of r. So without even taking a limit, the ratio at every step of the way is absolute value of r. And as we've seen, if this is less than 1, the geometric series converges. We know what it converges to in this case, but all that's important is that this converges. If it's greater than 1, we know it diverges. If it equals 1, it also diverges. But now what we're going to do is compare a general series, use a sort of comparison test, which again we haven't done yet, but we're going to compare with the general series with a geometric series, and unfortunately when it equals 1, the comparison doesn't work and you don't learn anything. But in any case, just be aware that the ratio test is a fancily wrapped up comparison with the geometric series. But man, it's a nice wrapper. This is a beautiful presentation because you can solve a lot of problems without much fuss. So what I propose to do is do a whole bunch of examples, which, as I said, are from 23.3, of how to use the ratio test. Before I do any examples, I should say one thing. Whenever you see a series which involves factorials, and actually we're going to be seeing a lot of these series coming up naturally when we do Taylor series and power series in a couple of weeks. So a little hint is always use the ratio test when factorials are present. And when I say factorials, I'll talk about them in a little bit, but think n exclamation point. It's also useful when exponentials are there, like 3 to the n. They tend to work pretty nicely too. But the factorials is a giveaway. All right, so let's look at a few examples. Here's a few first that don't involve factorials, a couple at least. So we'll take the sum from n equals 1 to infinity, n to the 1,000 over 2 to the n. Actually, you can use the limit, not the limit, just the regular comparison test to do this problem, and maybe, if I remember, we'll see how to do this next time. However, let's try to use the ratio test. As I said, this exponential here, 2 to the n, should be friendly. So here's how I'll set it out. I'll write down the words ratio test so that it's very clear that that's what we're starting to apply. We take the limit, n goes to infinity, an plus 1 over an, absolute value. And as I said, big fraction bar. And down the bottom, I'm just going to copy the term n to the 1,000 over 2 to the n. Bang. That's an. To get an plus 1, which is on the top, I replace the n by n plus 1 in parentheses. So I get n plus 1 to the 1,000 over 2 to the n plus 1. Actually, don't need parentheses there because it's already in a superscript. All right, so now what? Well, let's drop the absolute values because everything is positive. And we'll also invert and multiply so that the 2 to the n comes on the top and the n to the 1,000 is on the bottom. And if I group them appropriately, I have n plus 1 to the 1,000 over n to the 1,000. And then the 2 to the n comes all the way on the top over 2 to the n plus 1. That's good technique to amalgamate the like terms together from the ratio. It's also a good technique to group the 1,000th powers together. I get n plus 1 to the 1,000. As for the 2 to the n over 2 to the n plus 1 term over here, well, I can just cancel that in place, leaving me with 1/2. So down here, that's the limit. Now, n plus 1 over n is actually quite easy to deal with. You could even write it as 1 plus 1 over n. And however way you choose to skin this cat, that limit is 1. And so you get 1 to the 1,000 times 1/2, which is 1/2. We finally found the limit that we're looking for. Well, what does the ratio test say? It says we find the limit, and only thing that matters is whether it's less than 1 or greater than 1 or equal to 1. In this case, it's less than 1. So the original series, which we may as well write again, n to the 1,000 over 2 to the n, converges by the ratio test. We did not have to get our hands dirty at all with the actual series. We just looked at the ratio of terms, took the limit, and miraculously we get that the original series converges. Pretty nice. All right, let's look at another example. Actually, a few more examples. Okay, the sum from 2 to infinity, 3 to the n over n log n. Use the ratio test for this. Well, start the same way, ratio test. Limit n goes to infinity, absolute value an plus 1 over an is equal to the limit as n goes to infinity. Here on the bottom we have 3 to the n over n log n. On the top we have 3 to the n plus 1 over n plus 1 log n plus 1. Notice I've replaced every n by n plus 1 quantity. All right? This is, well, again, I'll drop the absolute values since everything is positive. And let's group it. We get 3 to the n plus 1 over 3 to the n. We'll have the n log n is going to come all the way on the top. So we'll have an n over n plus 1. And we'll have also a log n over log n plus 1. All right, so there's 3 different terms. This just cancels down to 3, no problem. It's pretty obvious to see that this is going to go to 1, but you might want to divide top and bottom by n to prove it. As for this, it's not obvious that it goes to 1. It is true, but it's not obvious. To do it, I'm going to change n into a continuous variable using that embedding technique I talked about right at the beginning. And I'm going to use L'Hopital's rule. So I'll just come over here in a little sidebar and just consider a continuous variable log x over log x plus 1. We have to work this out. Well, now these are continuous. It's an infinity over infinity case, so I can use L'Hopital's rule. And the derivative of log x is 1 over x. The derivative of log x plus 1 is 1 over x plus 1. And so we get the limit x plus 1 over x, which is surely 1. You can write it as 1 plus 1 over x. Therefore, the limit with x replaced by the discrete variable n is also 1. So coming over here, the limit is 3 times 1, which is 3. Only thing important about 3, it's greater than 1. So, the original series, 3 to the n over n log n, diverges by the ratio test. Nice. By the way, if you did happen to use the nth term test on this, so just look at what happens to these quantities, forget the sum, it turns out that they go to infinity because exponentials grow faster than either the polynomial n or the logarithm. So you could also just start by saying, hey, the nth term goes to infinity, not 0, so it diverges. So the ratio test actually is overkill, but on the other hand, maybe you don't know or notice that it's an exponential over a log. You don't need to. The fact that the ratio is bigger than 1 means that that nth term test will fail. So if you ever get a ratio bigger than 1, then maybe you should have used the nth term test, but it's no crime to use the ratio test instead. If you have any questions about either of those examples, shout them out. I've got a few more to do. All right. Consider this. Just consider 1 over n log n. is very similar to the one we just did, but we don't have the 3 to the n. In fact, it's so similar, I want to come back and look what happens here. Everything will be the same, except we don't have these 3's here. So we won't have this 3. But we'll still have 1 times 1. So you'll get the limit of 1 instead of 3. So, I don't know, if we come back over here and we do the ratio test, I'll leave it to you to write in all those details. So you'll get the limit equals 1. What do? You give up. Try something else. Ratio test fails. So even on something so simple as 1 over n log n, it fails. Actually, it would fail even on 1 over n. The limit is 1. 1 over n squared, the limit is 1. And yet, as we saw earlier, the 1 over n diverges, the 1 over n squared converges. So the ratio test isn't all that powerful, actually, when it comes down to it. To do this problem, you need to use the integral test, and that's something we're going to look at the beginning next time. So I just want to point out that although it's a lovely tool, it is not infallible. On the other hand, it really shines when factorials are involved, as I said. So let's spend a little time looking at how the ratio test interacts with factorials. So first of all, let me remind you that n factorial is the product 1 times 2 times 3 all the way up to n minus 1 and n. It's actually good practice trying to write down a few terms on either side of the beginning and the end so that you know what's going on. Now, here is a sort of important point. Often when doing the ratio test, you will come up with expressions that are sort of like this. N factorial over n plus 1 factorial. That's a very common sort of thing. This simplifies beautifully if you write it out properly. You will have 1 times 2 times 3 up to n minus 1 and n on the top. So that's n factorial. N plus 1 factorial includes all these numbers. As well as the last term, n plus 1. And so it simplifies dramatically down to 1 over n plus 1. Because all of this cancels. That's why the ratio test is so nice with factorials. When you've got whole lots of products and you take the ratios and a lot of the terms are in common, you get this mass cancellation. Another sort of wrinkle will be, and we'll need it in my next problem that I'm going to give you, will be something like this. Suppose you had to take 2n plus 2 factorial over 2n factorial. By the way, 2n factorial is not the same thing as 2n factorial. It is vital to put these parentheses in there. It just doesn't make sense if you write 2n factorial. It's a different thing. In any case, the bottom, I'll start with the bottom. This is the product of all the numbers from 1 up to 2n. So the last term is 2n. The second last term is 2n minus 1. So what about the top? Well, the top, product of all the numbers from 1 up to 2n plus 2, that actually includes all the numbers up to 2n, as well as 2n plus 1 and 2n plus 2. So if you do a big amount of cancellation, you are left with the product 2n plus 1, 2n plus 2. Again, this is not supposed to be an exhaustive list. These are two ratios that will happen to come up on the next problem that I do. The point is not to learn these formulas at all. Instead, understand how to derive them by writing out the factorial and doing the appropriate cancellation. All right, so this was preparatory for the following problem. The sum from 1 to infinity, 2n factorial over n factorial all squared. So these are both humongous numbers. Factorials grow much faster than exponentials, as it turns out. And exponentials grow pretty quickly. So factorials are bloody fast. They grow extremely quickly. 2n factorial grows quickly, and the square of n factorial also grows quickly. Let's see if we can make head or tail of this. By the way, we'll need it later. Just want to remind you, 0 factorial by definition is 1. So actually, I could have started this sum at 0, and it would have made sense. It would have been 0 factorial over 0 factorial squared, which is actually 1 over 1. But it doesn't matter where you start these terms, these series. So let's take a look at it. Factorials are involved, so immediately an alarm bell goes off in my mind, and I'm going to use the ratio test. So I take the limit as n goes to infinity, an plus 1 over an absolute value. So this is the limit as n goes to infinity. We need this big fraction bar here. And I'm going to have 2n factorial over n factorial all squared. The top, I need to be a little careful. I will have 2 quantity n plus 1, and then that quantity factorial. So you need all those parentheses. On the bottom, I need quantity n plus 1 factorial and that quantity squared. And there's no avoiding that. All right, drop the absolute values. Everything's positive, in these examples at least. And let's tidy it up a little bit. We'll get 2n plus 2 factorial over 2n quantity factorial, whereas the squares will come on the top. The n factorial squared comes on the top, and n plus 1 quantity factorial all squared goes on the bottom. Now we can simplify this a little bit. Not much. 2n plus 2 factorial over 2n factorial. We'll just pull the square around all of this and get n factorial over n plus 1 factorial, that fraction squared. And now, of course, we have to simplify these quantities here, and somehow those are exactly the two examples that I did up there. So at this point, you would go and do these two computations. First, n factorial over n plus 1 factorial, and then 2n plus 2 factorial over 2n factorial, in whatever order you like. And if you did that, you would get those simplified expressions, which I am now going to substitute in here. This is the limit, as n goes to infinity, of what? Well, this one worked out as 2n plus 1, 2n plus 2, and the other one worked out as 1 over n plus 1, but we have to square this. Now, this is just a polynomial over a polynomial. We can make life even simpler by factoring out n plus 1 from here and n plus 1 there. So we can replace this by a 2 and get rid of the squared. And so we can write this as the limit, as n goes to infinity, of 2 times 2n plus 1 over just n plus 1. And the leading term here is 2n over n. It's easy to just divide top and bottom by n or use the twiddle method to see that this limit is 4 as n goes to infinity. 4 is bigger than 1, so the original series, which I'm not going to write out again, but you should, diverges by the ratio test, which I resist the temptation of abbreviating it to rat test, because it looks dumb. Yes. You should also not abbreviate functional analysis to, well, the first 3 and 4 letters respectively, as happened on one of my undergrad tests. So, anyway, never mind that. We have here a divergence, and the ratio test did it for us. Now, as an exercise, if you put 5 to the n down the bottom here, which I didn't have in the original problem, and you try it, work it through, you'll find you get an extra factor of 5 on the denominator. So the limit will be 4/5. And that would cause it to converge. So even though the exponential here, 5 to the n, is much smaller then any of these, its presence causes the series to converge instead of diverge. On the other hand, if you only put 3 to the n, still not good enough. If you put 4 to the n, the ratio test will fail because this limit will not be 4, it'll be 4 over 4, and you'll end up with 1. Anyway, so that's more things to try. So what I want to do now is move on to the root test, but if I have time at the end, and I think that I will, I'd like to do one very difficult problem involving the ratio test and factorials, just to show you that they can get a little trickier. But I don't want to do that now because I feel like we've spent enough time on the ratio test for the moment. I just want to go and do the root test. So are there any questions about any of those examples? If so, you know what to do. The root test is very similar in a way to the ratio test. Instead of taking the ratio, so once again you've got this series that you're dealing with. Instead of taking the ratio, you take the nth root of the term. Take absolute values just to make sure everything's positive. Just take the nth root, and then take the limit of that as n goes to infinity. Very similar to the previous one, but you don't write an plus 1 over an. You write an to the 1 over n. Absolute values, just to make sure. Okay, so this is going to be the limit, and you just copy the term. You don't need to mess around with the substitution. Just don't forget to take the nth root. And you mess around and you hopefully get an answer L. And once again, mercifully, the 3 possibilities are the same as they are for the ratio test. If L is less than 1, the original series converges. If L is greater than 1, the original series diverges. And if L equals 1 or does not exist, test fails. You've learnt nothing. Use another test, not the ratio test. So you're going to have to do one of the tests from next week, or possibly the nth term test, I guess. Okay. Well, as you might expect, the problems or the layout of the solutions is quite similar. I should say that you should use this test when taking the nth root, when the nth root is easy to compute, since that's what you've got to find. So I'll just do an example of this. Not limit. Sum n equals 1 to infinity, 1 minus 2 over n to the n squared. Okay, before I go any further, I just want to comment that if the square wasn't there, so this was the problem, then it would be very similar to that nth term test example I did a little while ago. See, the terms would then go to e to the minus 2, and the thing would diverge by the nth term test. But with the squared, it's not so clear what that limit is. So I say use the root test because it's easy to take the nth root of this. You can tell because there's just an n squared on the top here. You know, if there's just a simple function of n in the exponent, then the root test is often a very good bet. So to set it out, I will write root test, and I'll take the limit as n goes to infinity of just the absolute value of an which in this case is the limit of, it's n to the 1 over n. Got to practice what I preach here. There's limit as n goes to infinity of 1 minus 2 over n to the power of n squared, absolute value to the 1 over n. Well, here in this problem, the absolute value is unnecessary once again because everything's positive. So let's just drop it. You get 1 minus 2 over n to the n squared, all to the power 1 over n. Well, our exponential rules say multiply the n squared by 1 over n, and this just becomes the limit of 1 minus 2 over n to the n, which we know is e to the minus 2, otherwise known as 1 over e squared. Didn't write that very nicely. Well, the important thing about this, e is bigger than 2, actually, 2.7 and a bit. So 1 over e squared is like 1/4, 1/5, 1/6, something like that. It's certainly less than 1. Therefore, the original series converges by the root test. Nice. Now what I want to emphasize is, if you try the nth term test here, you look at the limit as n goes to infinity of 1 minus 2 over n to the n squared. You don't look at the nth root of this, you just look at the limit of the term itself. So I just compare this to the 1 over n. Very different objects. Here you are using the root test, here you are attempting to use the nth term test. Actually, without even computing it, I know this must be 0. Why? Well, the reason is that I know from the root test that this series converges. So the nth term test must fail in the sense that the terms must go to 0. If the terms did not go to 0, the series would diverge. But it doesn't diverge, it converges. So actually that limit is 0. But that doesn't tell us anything. Even if you work this out directly using L'Hopital's rule type C all the way back from, chapter 14 in my book, you could work that out directly, and it wouldn't tell you whether this converges or diverges. Just knowing the terms go to 0 doesn't tell you anything. On the other hand, using the root test with that 1 over nth root, that's the crucial point. That causes the thing to converge. So, just by way of explanation, again, consider the geometric series. If you were to just take the nth root of the nth term, so the nth root of r to the n, absolute value, is actually the absolute value of r, the nth. You can pull it through, and if you really want to be gory about it, you write absolute value of r to the n to the 1 over n. So the absolute value of r. So you don't even need a limit. For the special case of the geometric series, that nth root is again the absolute value of r. And if that's less than 1, the thing converges. If it's greater than 1, it diverges. If it equals 1, it happens to diverge, but then your comparison, which is what's going on in the root test, will not work properly, and so the root test turns out not to work at all. So again, the root test is a fancy comparison with a geometric series. That's what it comes down to. And I should give some references from my book as to where to find out about this. The theory is in 22.5.1, and the problems, 22.5.2. The problems are in 23.4. I just did one example here. All right. So I still have about 10 minutes left, and I promised you a really hard ratio test problem. So what I'm going to do is clear myself some board space. I'm just going to work through this problem, and then we'll leave all the other tests for next time. If anyone has any questions about the root test, now would be a great time to shout it out. All right. Hard ratio test problem. The sum of n factorial over n plus 3 to the power n. All right, it's very tempting to use the root test because on the denominator here you can easily take the nth root. Unfortunately, the nth root of a factorial is kind of nasty unless you know something very useful called Stirling's formula, and we don't know it. So let us use the ratio test. And as I said, this is going to be tricky. Consider the limit n goes to infinity, absolute value an plus 1 over an. They all start this way. Okay, so we'll have on the bottom n factorial over n plus 3 to the n. On the top we'll have n plus 1 factorial over n plus 1 plus 3 to the power n plus 1. Well, again, everything is positive. All the examples, everything's been positive, but next time and the time after, I guess, I will talk about how to deal with series with negative terms. Anyway, so I'll drop the absolute values, do a bit of simplification. I will get n plus 1 factorial over n factorial. And I will also get n plus 3 to the n, coming over the top here, over n plus 4 to the power n plus 1. Gross, but that's how it is. One thing I can do is apply my factorial trick. Earlier I did n factorial over n plus 1 factorial. This is just the reciprocal, and I'll leave it to you. It's not too hard to see, in fact, the same trick that you get n plus 1. But unfortunately, we still have n plus 3 to the n over n plus 4 to the n plus 1. How are we going to deal with this? It's pretty messy. Well, it would be really lovely if both these powers were n. So let's pull out, this is a nice little trick, we'll pull out a factor of n plus 4. So we'll have an n plus 1 over n plus 4, and then what we'll be left with is n plus 3 to the n of n plus 4 to the n. And so we can group them together. N plus 3 over n plus 4 to the power n. Well, we still have a bit of work to do with the limit. There's a number of ways of doing it. The first thing I want to notice is that clearly goes to 1. When n is large, this is the limit as n goes to infinity, that quantity is very close to n in ratio. This is close to n, and so it's easy to see that that limit is 1. But this is the thing we don't really know about. So, as I say, there's some clever things to do, but the naive thing, and something that's going to work for sure, is to treat it as a L'Hopital type C. So I will change the variable from n, a discrete variable, to x, a continuous variable, and consider this limit. We want to work out the limit as x goes to infinity of quantity x plus 3 over x plus 4 to the x. Well, this is a case where both the base and the exponent involve x. So we better take instead the logarithm of it. That's the technique from chapter 14. Take the logarithm, x plus 3 over x plus 4 to the power of x. And we'll see if we can find out what that is. If we know this, we should be able to work out this. So this is the limit as x goes to infinity of x log x plus 3 over x plus 4, which I'm going to write as log x plus 3 over x plus 4 over 1 over x. So I'll pull the x down into a denominator which I'm manufacturing. And the beauty of this is that as x goes to infinity, this quantity, x plus 3 over x plus 4, goes to 1. So the top is log 1 in the limit. So that's 0. The bottom is 1 over a large number in the limit. It goes to 0. So we have a 0 over 0, and we can just use L'Hopital's rule. Before we do use L'Hopital's rule, however, I want to be quite sneaky, make it easier for us to differentiate by using a log rule and writing this as log x plus 3 minus log x plus 4 all over 1 over x. And now it's a pleasure to differentiate. Well, not quite, but it's nice anyway. It's not too bad. You get 1 over x plus 3 minus 1 over x plus 4 all over minus 1 over x squared. And there's a limit that we have to work out. Well, how do I deal with this? Algebra. This is the limit as x goes to infinity. X squared can come up the top. Actually, the negative x squared. And then I have to take a common denominator of x plus 3 and x plus 4. And on the top, I will get x plus 4 minus x plus 3. So that's just a simple little bit of algebra. What's left? Well, this all simplifies down to 1. So it's minus x squared over x plus 3, x plus 4. Well, this is just a poly over a poly. We could almost immediately write that it's minus 1. But if you want to be really clever about it, follow my technique from the beginning of the whole course, Math 103 at Princeton, or Chapter 3, 4 in my book. I guess you can write this as x plus 3 over x times x, x plus 4 over x times x. This x squared cancels out these two x's. And this is just 1 plus 3 over x. That's 1 plus 4 over x. So everything goes to 1, 1, minus 1. The limit is negative 1. Whew, a lot of work there. And we've still got to come back to the original problem. But let's just take stock. We have shown that the limit of log of this is negative 1. So the limit of the original quantity is e to the minus 1. That we have seen. If log of something goes to L, then the original thing goes to e to the L. So in this case, the log goes to minus 1, so that limit is e to the minus 1. Now, of course, we can move back over here and write this, change to the discrete variable, and you get the limit of e to the minus 1. And so our ratio in the limit is 1 over e, which is less than 1. Whoa, dodge chalk. So the series converges, after all. Pretty nice. Now, I'm almost done. I just want to show you something a little bit fancy. Still have 2 minutes. Something like that. How to avoid all that mess. If you are sufficiently inspired, you want to deal with this, right? Limit as n goes to infinity, n plus 4, or n plus 3 over n plus 4 to the n. Well, let's consider this limit. N plus 4 over n plus 3. What the hey? Why would I want to do that? Well, this is the limit as n goes to infinity of what? Well, I'm going to write n plus 4 as n plus 3 plus 1. So this is 1 plus 1 over n plus 3. All right, so this becomes 1 plus 1 over n plus 3, all to the power n. Now it's starting to look quite E-like. In fact, if I do something really silly, or clever, depending on your point of view, and write this as 1 over 1 plus n plus 3 to the power n plus 3, unfortunately, that's not quite true. I need to correct this into an n. So I'll do this by taking the power n over n plus 3. Well, what do you think happens to this? This is 1 plus 1 over large number to the same large number. It doesn't matter that it's n plus 3. We can replace n plus 3 by m in both places here. And so everything in this parentheses goes to e to the 1. As for this power, that also goes to 1. N plus 3 and n, the ratio is just, well, it's easy to see that it's 1. Just divide top and bottom by n. And so this limit is e to the 1, which is e. It's kind of tricky. Of course, that's not the one we want. The one we want is the reciprocal of it. But we just worked out that that's e, so this is 1 over e. You didn't have to use L'Hopital's rule at all. So, I don't know, that's just the inspirational way of doing it. There's probably other ways of doing it too that I can't think of off the top of my head. Anyway, okay, so we've made a good start for sequences. Well, in fact, we finished that, and we've done series as well. So next time, we'll continue the tests with the integral test and then all of the other tests that we've looked at. So, until then.